Science, Technology and Environment, KSCSTE, an autonomous body under the Department of Science and Technology, Government of Kerala, which was formed with the objective of adopting an integrated approach to the research and development activity of the center. The center has interdisciplinary expertise in traffic engineering, transport planning, public transport, highway and structure engineering, pavement engineering, geotechnical engineering, road safety, water transport, geomatics, transport economics and management. The center has 2 regional offices at Kozhikode and Ernakulam. The scientific and technical staffs are organized into 4 scientific divisions. The center's technical matters are governed by the Research Council and administrative matter by the Management Committee. So NATPAC has been organizing a series of monthly online lectures, TransTech Talk series, which is benefiting students, stakeholders, researchers, etc. The lecture series offers attendees an insight into the wide range of topics. The inaugural talk of the series was conducted on 10th February 2023, where participants from eminent institution, departments, etc. attended. The inaugural address was given by Professor Dr. Tom V. Matthew, Chairman, Research Council of NATPAC, and Professor IIT Bombay. The first talk in the series was delivered by Dr. Srinivas A. Pulugutta, Professor and Research Director of Department of Civil and Environmental Engineering at the University of North Carolina at Charlotte. The talk series was then carried forward by eminent faculties and experts. So today's talk, the 15th in the series, is organized by the Water Transport and GIS Division of NATPAC. The division comprises of 4 scientists. Myself, I'm the scientist in charge of the division and is assisted by Dr. Sabita NM, Senior Scientist, Veena KS Scientist, and Dr. Ramisha TV, Junior Scientist, and Shama, Library Assistant. The main activities of the division are to undertake research consultancy studies related to the inland water transport, coastal shipping, mobile application, and GIS. Today, we have with us Dr. Alfred J. Kalyanapu, the Professor, Tennessee Technological University. It is with great pleasure and enthusiasm that I extend my warm welcome to our distinguished speaker, who has graciously accepted our invitation to share insights and knowledge in the realm of development of low-cost real-time water level monitoring system, a case study of Falling Water River Watershed. On behalf of NATPAC, let me welcome you all for this technical session. And after the presentation, we will have a question and answer session where you can post your questions and engage in meaningful dialogue with the speaker. So now I hand over the baton to Veena KS, a scientist, to introduce the speaker.
Alfred J. Kalyanapu is a professor in the Department of Civil and Environmental Engineering at the Tennessee Technological University, USA. He received his B.Tech degree from the National Institute of Technology, Warangal, India, MS and PhD from the University of Utah in Salt Lake City. His research group focused on understanding the complex interplay water resources has with climate, urbanization, energy development, and how winter affects the sustainability and resilience of communities. Dr. Kalyanapu's research focuses on floods, hydrology, water resources engineering, and environmental modeling. He has published over 30+ peer-reviewed journal and conference papers and 90+ conference proceedings, presentations, and technical reports. He has received numerous research grants from federal and state agencies, including the United States Department of Agriculture, United States Geological Survey, Tennessee Department of Environment and Conservation, and National Science Foundation. With this brief introduction, I would like to invite Dr. Alfred Kalyanapu to deliver the talk. Over to you, sir. Thank you.
Good morning. Thank you so much for the warm welcome. Once again, before I start, I would like to thank Professor Samson Matthew, the director of your center, as well as Dr. Sabita NM for inviting me to talk with you all. First of all, can you all hear me okay? Just a nod should be okay. Can you all hear me okay? I'm not so sure. If you
Yes,
don't...
sir. Yes, sir. We can hear you.
Perfect. Okay. The next thing is, let me start by sharing my screen. I have a few slides that I made ready. I'm hoping that Within 20 minutes or so, we'll be done with the talk. It depends on how long I can speak, and sometimes I think Dr. Savita, no, I can speak a little longer. So if it takes too long, I apologize in advance. I'm going to start sharing my screen. Is that okay? Let's see. Please, would you confirm if you're able to see my screen?
Yes, sir.
Okay, perfect. So I'm going to start the talk now. The introduction for my research and my research group has already been done. Thank you so much for doing that. And once again, thanks for inviting me for the talk. As the title indicates, I'm going to talk about some of the research works that we have done over the past 7 years or so, and looking at bringing the cost of measuring water level down such that the water level is also available relatively quickly rather than going to field and downloading. So that's why it's going to be on the low cost and a real-time water level monitoring system. I'm going to show you an application to a watershed that is very close to where we live here in Tennessee, USA. But essentially, the system can be applied anywhere. So I figured before we start, it'll be nice. I don't know how many of you have been to Tennessee, but I thought I'll just share a little bit of compare and contrast between Tennessee and Kerala. Both of them are states. So the first, and these are last minute things. I've just shared them from Wikipedia. Okay, it's not thoroughly authenticated, so apologize if there are any inaccuracies. So nicknames. It's good that both of them have nicknames. I actually knew Kerala's nickname, God's own country. And Tennessee, the state of Tennessee, the nickname is the volunteer state. And if you look at the dates, obviously India as a nation has been relatively new compared to United States, but the state of Tennessee goes back almost to more than 200 years. The capital of Tennessee is Nashville, and currently Tennessee Tech, Tennessee Technological University is about 1.5 hours from the capital. So we are about 130 miles from capital. The state of Tennessee is about 710 kilometers long and 195 kilometers wide. Sorry, that's a typo. It's 195 kilometers wide. So it's mainly long on the east to west and short on the north to south. On that aspect, the state of Tennessee is larger. The area is almost triple the size, or maybe 2.5 times or so. The population, on the other hand, is a different situation, as you would assume for if you're comparing India with any other country. So we rank about 15th in the entire United States, whereas with almost 4 times the population, Kerala ranks around 13th in India. So there is that difference in there. And it's much more pronounced when we look at the population density here. So in Tennessee, on an average, the density is not that much compared to Kerala. However, all these also will influence how we design our engineering systems, right? Some of them are for fun, but some of them are actually, they have real world implications. I also wanted to show graphically how Tennessee compares with Kerala. So if you take the polygon of the state of Tennessee and rotate it about, say, about 200 degrees, or sorry, 110 degrees, and try to overlay it on Kerala, that is how it will look. And if we zoom in closer, that's the shape of Tennessee on top of Kerala. So as you can see, it's obviously bigger than it, but that is how it is. Okay. All right. So now that hopefully this gave you some introduction to the Tennessee as a state, and then let's move on to the actual topic at hand. So this is the actual north-oriented state of Tennessee that you see in the screen. So what you see here are the state boundary, obviously, and the polygons that you see are all the watershed basins, or we call them basins here. So the way watersheds are cataloged here in the United States is by using a code called Hydrologic Unit Code. And you can apply this hydrologic unit code cataloging system at various levels. So if you are applying it at a very large scale, as in the country or regional scale, it will be a smaller number. But as you go into a higher local scale, then the number will increase. So what you see here is at hydrologic unit code 10. So according to this scale, if you find out all the watersheds that are available in the state of Tennessee, and that's what you see. And then on top of that, the green hexagons that you see are what are called the USGS stations. USGS stands for United States Geological Survey. So that is the agency that is responsible for monitoring all the hydrologic information, and more than hydrologic also, but as it pertains to our talk, it's hydrologic information. So all those dots that you see have real-time water level, water depth, and stream flow information available. Some of them also have water quality, but that's outside of our topic for today. So that is what you see. First thing that you can notice is it's not less. There are a good amount of points that you can see. However, if you look closely, you will see that some of these points are actually clustered around certain locations. So for instance, let me see if I can change my marker to a laser pointer. If you see my pointer here, this is one cluster, this is another cluster, and there is another general cluster over here. The reason why you see that, it's not by accident. Those are all urban areas. So those are the city of Nashville, which is the capital city of the state, is right there. So as you can see, because it's a larger area, you have a lot more you have a lot more gauges over there. And there is the city of Memphis here. That's also one of the largest cities in the Tennessee state. So that's why you see a lot more concentrated here. And you have the city of Knoxville here. That's why you have concentrated here. Where we are located, the Tennessee Tech University is located, is right in this small polygon that you see. In fact, that polygon is the Falling Water River Watershed that we're going to talk about today. I wish I should have color coded it. But all we have for the entire watershed is we just have one data point. Along that river, we only know at that point what flow and what flow is. So using that, you can do forecasting and so on. But if you look much deeper into that watershed, you have a lot more tributaries. So you can't really do a better flood forecasting just based on that one point. So to better explain my point, I'll show you very quick statistics. Hopefully this will work. Yes. So the total number of basins at HUC 10 level is 272 in the state. Out of these 272, you have a total of 133 gauge stations for the entire state, just doing the basic GIS analysis. And looking at how many basins contains at least one USGS gauge, that's only 1/3 of them. So out of 272, one in every 3 of those basins has at least one gauge. That means the remaining 2 basins don't have any gauges at all. So if there are floods that happen in those areas, well, you're pretty much you have to just watch out, and which is not the best situation to be in. So that's the remaining 67% of those basins don't have any type of flood forecasting capability. So you have to do your own data collection and you have to generate all that. So this highlighted the need for establishing a lot more high frequency and highly distributed real-time stream flow gauging networks. However, I do want to make a case here. Each of those hexagons, those green dots that you see, cost about at least $10,000. So we're talking about a lot of money, $10,000, if not more than $20,000. Sorry, it is 11 o'clock at 11:30 at night, so I'm a little tired today, so I can't really do math in my head right away. So the point that I'm trying to make here is each of those points, each of those green dots are very costly to build. So if you want to have the state of the art, that is what you need to afford to do. So that's all the background, the justification of why we did this project. And looking more closely, in all these areas where we don't have gauges, floods still occur. That's because we actually collected evidence to make a case for this. For instance, this is a location near Cookeville, Tennessee, where the state of Tennessee, where Tennessee Technological University is. And we put in a bunch of cameras around these areas where we have streams. These are not very large streams. These are not comparable to Godavari or Krishna. These are very small compared to them. But as far as potential damage that you can generate, that's a lot. So if you look at this, hopefully you can see the video as I'm playing. So this is back in 2018, we installed a camera just pointing at a location. I will restart this video so you can look at this. I'll give you some context. All right, so let me start again. So this is around 8 o'clock in the morning. So on February 10th, 2018. So the staff gauge that you see here, that's about 1 meter high. Okay, so right now it is around half a meter, which is not that bad, right? You can walk through, you can at this stage, you can actually walk across the cross section. It's not that hard. However, that's at 8 o'clock. When you look at it, as soon as it's keeping up, 1 hour later, 2 hours later, we had rain. And then by 4 hours, it's completely gone. So now that's a flood because it's actually exceeded the banks and it was going, not at this stage, but it was going beyond the bank. And this is just a very small river, okay, called Pigeon Roost Creek, which is a tributary to the main river in the Falling Water River. This is one location. So another location, again, this is in another tributary within the same watershed. In fact, this is in a state park. It's called Window Cliff State Park or State Natural Area. You will see a lot more drastic situation here because this is back in 2017, November, in the evening, and these cameras just turn off at night. They don't really give night pictures. We haven't programmed it to give night pictures. So you'll see the next day what happened. So the day before, this is how it was. Again, the staff gauge, this one I believe was about 4 feet or 5 feet. So the next day, we woke up to this. So on November 6th, we saw, at 4 p.m., we saw the video, but on November 7th, around 6 o'clock or so, we saw when we downloaded it, obviously, this was not real time. We had to go into the field and download the data to actually see what happened in the flood. But the point here is not only is the water level significantly higher, but the current at that location was so high that it was actually damaging. I don't know if you go back to this, well, the debris was here. This debris that you see, the wood and the trees, were from the previous storm. So, all right, so I'm going to quickly go here and then again, there was sudden, in this location, the water depth maybe not that high, but the rise of water was significantly higher. Sorry, I had text here. Oh, there it is. Okay, so the bottom line here is, as I mentioned from the map that you saw, as well as this video evidence, which when we showed it to the park rangers, they were shocked because people actually walk across these water bodies. So if a flash flood were to occur, in fact, I don't know if you can see this, but this is actually a pathway before the debris came in. So visitors to the state park actually walk through here. That's one of the features of the state park. So when we showed it to the park rangers, they were shocked and thankful at the same time because now they can share this with actual public to see the dangers that people can have if they are going without any particular plan along these watersheds and along the state parks. But the bottom line is, from a safety standpoint and even from a watershed management standpoint, you need to have more eyes on the water bodies. And then on top of that, you have to have cheaper options to do water monitoring, not something that costs $10,000, $20,000 per year to do that. Then we also want them to be, even if they're not state of the art, we still want them to be real-time data. As soon as we have, we get that. That's what we want. And we can achieve all these things by applying and using existing, not only existing technologies, but also new technologies. So these are all the needs, and that's what gave us the incentive, or actually the motivation to do this project. And we wrote a grant to the United States Geological Survey, identifying the need for this, and we gave Falling Water River as a case study that we can develop this system. And again, our objective was two things, mainly two things, but a lot of other things as well. Cost should be low, and it has to be real time. And now, even though I say stream flow, we are essentially monitoring the water level. And later on, that water level can be converted to a stream flow using rating techniques. But in this case, it's mainly stream water level is what we do. So to achieve this task, or to achieve this objective, our task was first to actually develop some prototypes, make sure that they work, and then test them out not only in the laboratory setting, but also in the field setting. Then start, once they're successful, start implementing them around the watershed. So for these tasks, I'll introduce the watershed to you. I know I pointed you that one watershed in the state map that falls right there. And when you look at it further down at HUC, so the blue polygon that you see, that is HUC 10. And these all individual polygons are within those things. So for this watershed, these are all sub-watersheds. So these sub-watersheds are at HUC 12 level. And at those HUC 12 levels, the blue lines indicate all the streams that drain into the main outlet here at the mouth of the watershed. So to give some orientation, the color that you see here, these are the city limits of Cookeville, and Tennessee Tech University, our university is right over there. And we have some smaller towns nearby. So in this, we have been working on this watershed for a while, even before we started the project. But the green and red star that you see, that is the location where our current gates, that one data point that I showed you, the state-of-the-art equipment, that is where it is. And we tried to work with the state government and other local agencies to install some offline sensors at those three locations. And later on, those were the offline stations. We were able to collect some data, but our motivation through this project was to implement real-time sensors throughout the watershed as much as possible. So for the first task, we looked at the potential ways to build the sensor, and we arrived at a prototype like this. We started very crude and very simple and very basic. As you can see, we were using pieces of cardboard and those small wires and connecting all those things. And we identified this particular thing. I don't know if you can see my cursor here, so I'm going to show this. So this one, that is a microcontroller. So for those of you who might not be familiar with it, it is equivalent to a small computer. And the advantage of that microcontroller is it has an embedded SIM card in there, so that if you program it correctly, you can not only make it do things for you, but you can actually transfer data from where you are to the into the internet. And then through internet, you can actually publish data on your data servers and so on and so forth. So we really were excited about using this, and we ended up using this. And we also have other components. We have some capacitors and resistors I'm not going to talk about, but I'm going to talk about this particular thing. I wish we moved it, turned it other way, but this circular disc looking thing that you see, that is the one side of the ultrasonic sensor. And we will have photos in the other location where you can see the full box. So we tested multiple options of water level sensors that you can use. And these sensors are not something that you install underwater. You actually put it over water. So these are indirect measurements. These are not direct measurements like pressure transducers that you use. And we also wanted to come up with a prototype such that it is all enclosed in a box, and we'll be putting this box in the environment, right? Like subjected to potentially harsh conditions. So we wanted to make it weatherproof as well as waterproof. And we also wanted to not only have a battery, but also have a solar panel so that that battery can be charged. So it worked out really well. and then I'm speeding the topic here so we can come to the results. So this is the flow chart. So every 15 minutes, we programmed it in such a way that every 15 minutes, this microcontroller will wake up, and then it'll talk to this sensor, take a distance reading, basically how far the sensor is from the water distance, and you can convert that distance to water height, and then publish that information to this microcontroller's cloud platform. Once it's there in the cloud platform, there is something called a webhook that we use so that our cloud hosted real-time data service. So this is our data repository. So from this repository, we hook the data and get it. So every 15 minutes, we send this webhook, get it, assuming that we have the information. So if the sensor is not awake, then we don't have the data. So even though we have a hook, that would not work. But most of the times it works. Well, actually, all of the, that we design it to work. So once we save the data on our cards server, you can then visualize it on a dashboard type setting. So that is how it is. Again, I'm going very high level. I'm not going into too much detail. So I did not design this. I'm not an electrical engineer. So I'm a civil engineer. So I had electrical engineering students working with me, and we designed a lot of options. This was the final product, but we had to do some tough choices. We had to have some issues. We got some issues, and eventually we ended up with this. This is the circuit for the what our sensor is, and based on this circuit, we actually printed a circuit board such that instead of using a bunch of those wires that you saw in the previous image, you can just hook up these small end connectors and then connect our sensors to it. So that way it is much more cleaner. And then this is the code. The code, it's a C++ C code, which when we compile it, will convert that to the binary that the microcontroller will use. Yes, so this is again one of our initial prototypes that we had. What you see here is you have an LED. You have a screen here. We did not put the screen in our finalized version, but this was just for initial testing and so on. And you also see a red board at the bottom. We did not end up using the red board. We actually designed our own board to do this. So anyway, so we had a bunch of options we started with. This was one of our solutions to do. We tested it in the lab. So essentially what we did is we ran it, make sure that we are getting accurate results, distance measurements from those sensors, which gives us an idea that yes, this is correct. And then once we did the lab scale test, we took it outside where we put the box, right, and put under it a bucket of water. We know the water depth and we know the water distance, and we measured it, and we did the lab scale / field scale test like this. And we did this for multiple days. So we would take it outside, put it all day long, get all the data, don't know the measurements, and do compare and contrast. So that way we know that it's consistently giving us answers, correct answers. And once all the lab and field tests were done, we deployed it in the field. And these stars that you see in the map are where we initially installed. Now, mind you, the current state is different. It's currently, this was a few years ago. We have some new locations that were added and some of the old locations that were taken as well. So this is one of the locations. It's called Adams Acres Road. That is right over here, upstream in the headwaters of the watershed. It's a smaller bridge, but even though it's small bridge, that's not small. It actually floods the whole area. Water, actually, yeah, that's Ethan. Water, if it flooded at high levels, Ethan would not be seen. He would be underwater. So that's how high the water gets. So we actually learned that firsthand, because the first day that we put in, the water level rose so much, so very close to it that it might have briefly flooded the sensor box itself. So later on, we moved it away and kept it up. This is right after a flood that we had at that location. I was able to take a video of that. Oops. Let me show you the video. Hopefully. think yeah, this was after the peak times. But you will see some of the debris that we retained. This is some of the debris that you see that we retained. So the whole bridge was underwater. And the water current was not that small. It was actually pretty swift current. So this was what we did. We put in an aluminum pole and raised our sensor box up, and then had a boom where our sensor is right there. So our box is here and our sensor is right there. And that is what is being used. Currently, this station is offline, but we got data from this sensor for a long time. So this is the photo of that. And this is the data that we got back in 2019, I believe. You see the small dip, the sudden dips are sometimes, because it's an indirect sensor, you might have spiders go there and have their web and so on. So you might have some of the signal drop-offs there, but for the most part, it's been consistent. And you see the small loop that you see, the small diurnal patterns, that's normal. You always have that, even if it's a direct measurement versus an indirect measurement. But the peaks are what you need to watch out for. So in general, you are at low base flow, but this is the peak flow. It shot up more than 20 feet, actually 15 feet. 15 feet, so that's about 5 meters. That's pretty high for that level. And it happened back to back. You had some big peaks back to back. So this was one of those areas that I wanted to show. And then we had another location along a tributary to the Falling Water River called the Ditty Road Bridge. We started using this, but in the end, we had some issues, so we changed the configuration. So you will see that between this box and this box, it's significantly different. That's because we had some moisture issues in this box. We didn't realize that even though we tightened it so much, that the expansion and contraction of the air inside the box actually increased the cracks where we put the glue or the caulk on. So we changed our design and we actually put in pressure vented cables, cable glands, which some of the environmental extreme boxes you'll see. So that seems to be working really well. So this is the sensor that we have. And we also made different versions of the way that we have. So if you notice, we try to make our sensors small enough so that you can put it right next to a culvert or right next to a bridge and just drill a hole into the bridge or a culvert and it will stay there. And it doesn't really weigh that much, probably about half a kilo to 1 kilogram. So that's it. 1 kilogram is just too much. It's less than 1 kilogram. And for places where we don't have any structures nearby, you can create your own structure. So this is a cantilever beam that we created just using wood that we got from a local hardware store. And these are our students, and we are civil engineers, and we have civil engineering students. So they just built the whole thing. They just dug up hole, put concrete in, put those wooden beams, wooden pillars, and then put the beam out. So this is how it looks. We projected it further out and it's pointing the water level. And it's been stable. It still is there. We just haven't had a chance to go there. But this is another location where we use the same approach, but you can see that the bank is pretty active. That's because this is a very channelized river, and whenever it floods and it has significant flood, it carries a lot of sediment, so some of the bank is also eroded. So that's why you see all the erosion that you see. However, we had to, because of all the erosion, the initial plan was to put our sensor right at the end of the wooden beam, but it was no longer underwater, so we had to think on the fly. And by the way, this location is in another state. It's in Kentucky, so that's about 500 kilometers or so from where we are. So whenever we go there, we actually plan and go for 1 or 2 days. So when we go there, if you forget a small screw or a nut, you can't really travel 500 kilometers back. So that's why we had to think on the fly. So we actually extended this wooden beam with another aluminum beam and projected our sensor so that it is pointed to the water. This sensor actually really helped our project because using this information, we were able to figure out when that area flooded, because we were also doing some water quality calculations. Based on this sensor, we were able to plan our water quality sampling trips. So this is another look that I mentioned. We use aluminum slotted steel, I guess not aluminum, slotted steel to do this. So this is how it looks. And we got a lot of data from this, and this is one of the snapshots of those data. You will see that the water level rises suddenly, and in some cases like this, it stays flooded for a lot of time because that is in a wetland. It's designed for the water to stay at such high peaks at some locations. So that's why you see the almost like that tabletop structure that you saw. So this is another location that we have. And this is the location where we have the USGS gauge, the state-of-the-art gauge. And then the one on the back is what it is. And this was our initial gauge that we put in at this bridge. And believe it or not, both these gauges got flooded. Actually, 2022 is one, I think it got flooded. So it's not operational currently, but we raised the sensor up much higher so that it would not flood. But it did happen. Thankfully, what happened was we were able to collect the data from our sensor before it got flooded. So then my goal was to prove that even though the sensor that we designed is small and low cost, it still gives us accurate results. So that was the reason why we installed a sensor right next to this, their USGS gauge. So the red line here, the red color here shows the real-time data that our sensor is providing, and the green data is from the USGS gauge. As you can see, for the flood that happened in 2020, it was pretty close, and we compared the statistics. We did NASA cliff efficiency. Essentially, that tells us how close they are over a period of time. We also did the coefficient of determination that gives us how well correlated they are. Then we also looked at the percent bias between these two data sets using the USGS data as our standard. And it was a low enough percentage bias, and the scales of very good and good were taken from Moriasi et al. To 2015. They have a table where they suggested that based on whatever you're measuring, you can use these ranges. Based on the value that you get, you can pick a range and determine whether it's good, bad, or very good, and so on and so forth. And the root mean square error that we got was 0.3 feet. So that's about 1/3, like 30 centimeters or so, which was very good compared to it. And I just realized I talked about it being low cost, but I did not mention the cost. So compared to the $10,000 state-of-the-art sensor, our sensor only costs around $500. So that's about, you can do the math, right? So that's significant difference. So if you use $500, you can do the same thing as a $10,000 would do. So that's the price difference. And all these materials you can buy from Amazon, or you can buy from any website. You don't have to order from a commercial vendor. So to conclude, we did determine that the cost-effective solution was successful, and it was you can use that in potential flooding situations. I did want to say that yes, the state-of-the-art equipments are costly because of a certain reason, not just somebody decided that they just charge a large amount, but it's more costlier because a lot of engineering and science has went into it. There were a lot more tests that were done. There were a lot more robust design that went into it, and other IP issues that I don't have a lot of information on. So I want to clarify that we have our low-cost sensors, but we don't want to say that we will replace all the commercial sensors with these low-cost sensors, because this is just, after all, a research-based product. It's not a commercial product like a commercial gauge would be. So it's not a replacement. It's just adding to what we already have. The best thing that we can do is if we can put as many boxes as possible. If you think about the map that I showed, this map, the best thing that we can do is if we can put as many boxes as possible in all the polygons where we don't have a dot, at least now we'll have a better picture of, in this case, state of Tennessee, or in your case, the state of Kerala, whichever that is. Okay. And then the preliminary comparison that we did with the USGS data was very promising. So we continue to do that. We actually published a paper on it, and you can find that. If you don't have access to that, let me know. I'll provide you that information later on. So currently what we're working on is we're working with our county, which is equivalent to our district where our city is in. And we install additional sensors within the county doing the same thing essentially, so that the county emergency managers can know which roads will be flooded during a high rain event and so on and so forth. So it's much more focused on the county. And in addition to the low-cost real-time water level, we also have developed a low-cost real-time tipping bucket rain gauge. This is an example of what it is. I'm sure you must be familiar with the tipping bucket rain gauge. What we did is we took all the old technology and just replaced that old technology with our sensor, with our microcontroller, and it works fine. And we are currently in the process of testing our low-cost sensor with a commercially available rain gauge, and that one is ongoing right now. We also have done some basic work on low-cost real-time water quality, but I have to say water quality monitoring is much more trickier than water level monitoring. So we've done some work, but not quite. We are mainly focused on the water resources side of it at this point. And these are that's Dr. Datta, who was working with one of our graduate students when we were developing the low-cost water quality data sets. So currently, I should probably have shared this, but so all the data will be available. I mentioned about a way to show the data. So in this case, this is where it is. So this is the dashboard, and this is one of the locations for Putnam County that we have. It's an interactive dashboard. Well, actually, I don't know if you can see this. Oh, you are seeing it. Okay. So it's interactive, so you can go back in time and look back at all the data. For instance, this one right here. By the way, I have to say it's a dip. So for this particular site, we didn't convert that to depth or water surface elevation. So it's just the distance from the sensor to the water level. So if the distance falls down, that means it's a peak. It's a peak in a hydrogram. So that's what it means. Maybe I'll show you another one here. This is one of the recent ones that we did in another county in Tennessee. Let's see. I'll show you this one. So these are some peaks. So this location on the left-hand side is on an upstream location where the water, it's on a major river. That upstream location on one end of the county, and this one is on the middle of the county. So the idea on this one, this is ongoing. I'm working with the Lincoln County emergency managers to help them determine how long it will take for the water peak to go from the left bridge to the right bridge, so that they know what time they have for any type of evacuations that they can do. So, but the point that I'm trying to make here is the dashboard is available that can be used. So once we build our maps, build our sensors, we can show the data in our dashboards. And as needed, we can also make real-time GIS maps as well. And currently, I'm working on adding more gauges in the state of Tennessee. But as Dr. Savita might say, we tried to do that back in December in India, in Warangal. That project is currently ongoing. This year, we'll be working on developing similar gauges in an Indian context. Unfortunately, the microcontroller that we are using here in US is not able to work in India, because in India we still don't have narrowband IoT provider available as widely as we have here. So the internet connectivity that the small microcontrollers use is not similar to a cellular connectivity. It's different. So that's why it would not work. So that's why we couldn't do it in India. However, we found I think we found a workaround solution. So this summer, we are going to try to implement a sensor like this in Warangal. And once that works, then that will open up opportunities for us to do low-cost water level sensing outside of the United States as well. And I'm always looking to partner with people, not only in US, but also outside of US too. These are some of our partners locally here in Tennessee. And I want to again thank NATPAC and Dr. Sabita for reaching out to me. I know it's been a while. My response has been slow, but I really appreciate you in just persevering in that. And thank you so much for listening to my talk. These are some of the references that I have. Now I'll open it up for any questions.
Thank you, sir, for the informative and engaging session. The floor is now open for the questions.
Sir,
Yes.
hello. Sir, can you explain about the sensor that you use for this setup?
So let's see. Are we talking about this one? Can you see
Yes.
this? Okay. So what we have here is we have a microcontroller. Like I said, it has essentially it's a computer, but it's a very small computer. It does not have a hard drive. It has some memory, and that's it. And it has a small processor. But what it has is it has a SIM card. It's an embedded SIM card. So it's a computer that's connected to an internet. It's a small computer that's connected to the internet. So, and it's a computer that you can actually program to do certain things for us. So the sensor is in such a way that it can connect to, or things can be connected to this microcontroller. So this ultrasonic sensor is connected through this circuits, this confusing circuit that you see, in such a way that when we program it to wake up every 15 minutes, it will wake up. When I say wake up, it's not completely off. You don't turn off the computer. It's just in a almost like a sleep mode in a computer, right? But it has a clock that goes underneath that tells it to wake up every 15 minutes. So it wakes up, it gets it pings the sensor, it will measure the distance, and then it converts that into appropriate units, and then it publishes to our website here at cardzap.tendec.edu. That's it. And then it does that every 15 minutes. And this is how this is the what we have. We have a capacitor. We have some. I don't know if you see. Oh yeah, everything else that you see here. This is just where our microcontroller goes in. So this is as simple as the circuit goes. And this is just a screenshot of the code. I hope that answered your question.
Yes, sir. Thank you, sir.
You're welcome.
So I have a question. So you're telling that these instruments are being kept on the field. So is it that the data is being available on the go, or need to collect in the field? You have to go back and then collect it from that sensors. How that happens?
Right. Okay. Thank you for the question. So as I mentioned, so because it has a SIM card already inside the microcontroller, as soon as it measures it, it sends it to a website. So it's not stored on the local machine, on the local sensor. So you don't have to go in person and download the data. It's already sent. So that's the real-time part that I'm saying. So once you measure, you send it to a website real-time, so you have it. For instance, if you go back to this stage here, so if you look at this Lincoln County that I mentioned that recently, if you look at last 2 days, this is what it is. So if you look at the last 30, let's say 1 hour. So in the past 1 hour, all this data is coming in. So every 15 minutes, this propagates. So currently it's about 11:50. So by 12 o'clock, you'll get one more point here. So it's all real time. So you don't have to go to the field to collect.
Okay, thank you, sir.
You're welcome.
Samson, sir, are you here, sir?
Yeah, I'm there. Alfred, thanks for a full lecture. I'm audible?
Yes, sir.
Yeah, okay. Good. It was a good presentation. It was just looking that one. I have a small question now. Alfred, is it audible to you?
Sorry, sir. Can you say that again?
Yeah. You know, like, see how we can extend this concept. There are the road network, like especially in Kerala, probably we have the road network. We have like a hilly terrain and other, like, the network is there. And there are cases where it will flood during the monsoon season. How we can alert the system, like this is the water level, or this is the expected flood level. How we can monitor that one, so that we can take some advanced measures, so that people will be protected, or or other required actions we can take. Can you extend this concept to the road network?
Okay, I think, thank you for the question, sir. And thank you again for inviting me. I appreciate that. So to answer your question, I think, yes, we can develop, or we can have a network of these sensors along certain roads that are near water bodies that are prone to flooding. And then as far as implementation goes, as these sensors collect more data, you get a stream of data that looks like this. And say if you take two locations along a road, or along a river, if this is the upstream location and the downstream location, over time, as you collect data, you will actually see the impact of how upstream and downstream are related. Now it depends on a lot of other issues as well, but once you're able to establish that correlation, then you can determine that if the site hits a certain number, certain value, then that particular road is flooded, or if that will be flooded, and so on. For instance, if you look at this picture here, there is this, let me turn this off. So, oops. There is this bank full. So what we did was, at this location, we had somebody go and survey the elevations, water surface elevations, and we put that here on the dashboard. So we know if the water level reaches this location, then it exceeded the bank of the river. So now when we look at this, now we know, oops. Now we know how many times that the water level exceeded the bank full level. So similar concept can be applied. You can do some surveying, get established elevations of what you are interested in that will trigger any type of response in terms of flood fighting goals. And then you can apply, once you have this information, you can put it in a dashboard like this, and then you can visually do it, or you can also programmatically do it. You can write code to download the data and then do a comparison and just flag and send an email or a text message if a certain value has been exceeded. I hope I've answered your question.
Yes, Alfred. Now I have another question. See, there are especially not in Kerala, probably in northeastern part of India, there is a possibility that the river may during the flood time, it will identify a new route, probably unexpected fresh route it will identify. In such cases, how your the concept we can use.
Well, that would be beyond the ability of this sensor, because all this sensor is doing is at its location, it's just measuring the distance that water level rises to. So if the water goes beyond the main course and finds an alternative course, then this sensor is not smart enough to detect just by one sensor itself. However, if you have a vast network of sensors, then possibly, depending on how the water levels are changing, and also based on their locations, you can probably come up with a continuous map that will determine the path of the water that it can take. One close example is maybe it's not in looking at a riverine scale, but maybe looking at an urban area scale. So if you have stormwater flooding that you can put in these sensors at a high density setting. That way, you know what water levels are at each stormwater outlet or at each street. So you can determine which streets are flooded, which streets will be flooded, and so on.
Yeah. Yeah. Thank you, Alfred. That was
Thank you.
fine. Maybe it may not be. Yeah. Probably, listen. I thought probably we can integrate the remote sensing concepts also to that one.
Yes.
There are practical issues.
Right. Right. You can definitely integrate remote sensing and you can integrate hydraulic modeling, but it will just have to be done outside of this sensor itself. As I said, it's a small microcontroller. It doesn't really have a lot of computational capability than just to wake up and take a measurement. Now, we are actually seeking opportunities where we can do what is like edge computing type solutions, where you can have another computer somewhere nearby that is able to get data from here and get data from other sources, and then synthesize all of that and come up with additional modeling. But again, there is additional modeling that needs to be done, not just the data collection itself. But there are ways that can be done.
Yeah. Yeah, Alfred. Probably Ernakulam office. Ernakulam office probably listen. No, what is that? Your plan for that Ernakulam region, like the flood monitoring? Anish or Demisha probably can discuss with you. Thank you, Alfred.
You're welcome, sir.
Hello, am I audible?
Yes.
Yes, sir. So it is a good presentation, sir. So as the director was saying, in Ernakulam office, we are trying to talk to various stakeholders, and then we're trying to come up with a integrated solution wherein the water levels, if it is raining also, it gets flooded, the roads get flooded. So in such a case, we need to spread awareness about which all roads are capable of being used by two-wheelers or might be by cars. And if such an information can be given on a Google Maps or something of that sort, that will be very useful to the general public rather than one agency being doing this whole thing repeatedly. So it needs to be a real-time sort of a solution. So we're in talks with various stakeholders in this regard. And I had a few doubts, sir. In these sensors that you're putting in, do they consider a global datum, or is it the local datum that is being considered and then it gives us the data? And also the second question would be that do we have any subsidence or some change in levels that could be that could arise in a stretch of time, because there could be subsidence or the wind also can act and then the datum can change. So there are some, is there any correction factors applied or anything of that sort?
Thank you so much for your two questions, Anish. I'll try to remember the two questions and answer. The first question that you said was about water surface elevation or the datum that was used. Is there a global datum that is used, right? Okay. So
Yes.
to answer that, let me show you. Let me see if I can show you. I'll just show this one. Yeah, you probably didn't see this one because it's a different location. But what you see here is we install it, right? all the sensor is doing is this cone is doing is it is pinging sound waves at about 13K frequent hertz, 13K hertz, and it's getting back the return, and we're converting the return and using the sound wave to measure the distance. So as far as this sensor is concerned, it does not know what the datum is and so on. It just gives us a distance value. So what you see here in the value here is we take the data that it provides us, the raw data that it provides. When we put it in the dashboard, that is where we convert. So this is where we apply the datum conversions. So a short answer to your question is we are using the datum, mean sea level datum, the elevation of the site with respect to mean sea level at that location.
Okay.
So that's the first question answer. And I forget what your second question was.
Is there any subsidence or any effect of the wind or something of that sort? Are there any correction factors that are applied?
Very good question, especially in situations something like this. So where you have extra info, you don't really have a strong support to hold the sensor. In that case, you have to regularly go survey, make sure. When I say regularly, I would say a seasonal. I would go every flood season, go and make sure that the sensor is at a proper elevation, it's level, and it's pointing vertically and so on. So you have to do those field type maintenance work at a regular level, whatever that operating procedure that you set. But yes, otherwise, if you don't do it, it can change, it can dip, or it can even change angle and so on. And then also just the ultrasonic sensor itself, the signal can vary over time. So you might, after every few years, it's a good thing to calibrate or check the performance of this sensor just doing calibration.
Okay, thank you. Thank you.
You're welcome.
Is there any other questions?
All right. Well, before I forget, I do want to acknowledge my co-authors. I say co-authors, but they are basically my students who have helped in building these boxes, because it's all we have done. All we did was from the university. We had undergraduate students and 1 or 2 graduate students who helped in doing this. But mainly it was all driven by student effort, and I was able to harness all their creative energy and physical energy as well towards this project.
Okay, thank you, sir.
Thank you, Dr. Alfred Kalyanapu, for delivering such an enlightening session. Now, I would like to invite Dr. Sabita Ennam, Senior Scientist, Water Transport Division, to deliver the vote of thanks for today's session.
Thank you, sir. On behalf of KSCSTE-NATPAC, I would like to extend my heartfelt gratitude to each one of you who attended this session for this insightful talk on the topic development of low-cost real-time water level monitoring system, a case study for Falling Water River Watershed. It has been an enlightening and thought-provoking session, shedding light on a solution to one of the major problems faced by the hydrologists all over the world, like the availability of the data, or the lack of availability of the data or the resources for collecting data. So here we heard about the use of low-cost environmental sensors and development of a real-time sensor networking using Internet of Things devices for the stream flow monitoring. So first and foremost, I would like to express my sincere thanks to our esteemed speaker, Dr. Alfred Kalyanapu, whose expertise and knowledge have extensively captivated our audience. And actually, I would like to extend my thanks to him for taking some time of his busy schedule and attending this on late night for him. So I thank you, sir, for accepting our invitation and replying to our mails, repeated mails. Like and be here for sharing such a extensive knowledge and tried and proved technology with us. And I would also like to express my gratitude to all the attendees for your presence and active involvement. And also, I would like to thank our director, division heads, and other organizing team members for their meticulous planning and coordination for the smooth conduct of this program. And in conclusion, I believe that this session would be useful to many of you. I expect that this interaction and collaboration we will take forward, and we will achieve some fruitful results also. Thank you, sir.
Thank you so much, Dr. Sabita, and thank you all for attending and listening to me and have all the questions.
Thank you.
Thank you, sir.
Thank you, Alfred. Thank you. Good luck.
You're very welcome, sir. Thank you. All right. See you all.
Good night, sir.
Good night. Bye.